Yes, Professor. Good morning. Yeah,
Yes.
yeah. Good morning, everyone. We are at day three, and today's talk is on phasor measurement unit and applications. I think, Professor, you can go ahead. For
Okay. Okay. Thank you. Yes. So this morning, I think we have two sessions. Right? I will cover phasor measurement unit. Then after that, Professor Kumar will cover power converters in smart grid applications. All right. So let me share my screen. Okay. So yesterday we have introduced the advanced metering infrastructure (AMI) as well as the smart meter, and we have also introduced two typical applications of the smart meters. One is the price-based response. The other one is the non-intrusive load monitoring. Okay, so both of them applications are for the customer. Okay, because the smart meters are installed at the customer site. Differently, the phasor measurement unit actually is installed at the power generation plants and the transmission or distribution networks. So most of the PMUs are actually installed at the high level transmission network because the function of PMU to collect the wide area synchronized measurements. But sometimes there are also PMUs installed at the distribution network level. In this case, that is called micro PMU. Okay, micro PMU. Back to several years ago, I was involved in a special session of IEEE transaction on smart grids, and that special session is all about micro PMU and its application in distribution networks. Okay. So today I'm going to introduce the fundamental principle of the PMU as well as its major application for power system dynamic studies. Later on, I will introduce some of our own research works on this topic using PMU for power system stability assessment. Okay, so before we introduce PMU, let's take a quick look at the traditional SCADA system. Okay, SCADA stands for Supervisory Control and Data Acquisition. Okay, so this SCADA system is a standard configuration for industrial system because it has to collect the data of the system, transmit the system back to the control center. So this is a very fundamental infrastructure for an industry system. However, this SCADA system does not have a very high sampling rate. Basically, it will sample a measurement every 2 to 4 seconds. Okay, compared with PMU, this sampling rate is much lower. But compared with the smart meter, you can see the sampling rate is still considered very high because the purpose of the SCADA is to support the system's monitoring and control as well as operation dispatch. So basically, for the SCADA system, it will measure the voltage, three-phase voltage, and the three-phase current using PT and CT respectively. PT means potential meter. Okay, potential meter. That is to measure the voltage potential of the different phase of a transmission line or a bus. And the CT means current meter. Okay, it can measure the three-phase current. Then clearly, these PT and CT, they are analog meters. Okay, so the signal, the output of these meters are analog values. And after analog circuit, this meter will be converted into voltage magnitude and current magnitude. And since we have voltage magnitude and current magnitude, we can also calculate the power, right, including real power and reactive power. Okay, so To summarize, the SCADA system mainly measures the voltage magnitude, real power, and the reactive power. Okay, and these signals are generally transmitted through modems, microwaves, or internet, or power line communication, power line carrier communication, directly to the power system control rooms. And after receiving this voltage, voltage magnitude, real power, and the reactive power, the system control center, they can do the system dispatch. They can also do the security analysis. They can monitor the voltage and the line power flow, okay, in order to make sure that the operation limits are satisfied. So that is how SCADA system is applied. But there are a lot of inadequacies of the SCADA system. So especially for the large-scale power grid, okay, large-scale power grid, which may cover hundreds of kilometers or even 1,000 kilometers. I suppose in India, from the north to the south, it covers several thousand kilometers, right? So the SCADA system, they can only measure the local data. For different locations, unfortunately, the SCADA system does not have a synchronized timestamp. In other words, the data measured for different locations of the grid are not stamped precisely at the same time. Okay, for example, for one substation A, the measurement was taken at, let's say, 10:30 0 second. And in the meantime, another SCADA system measured at the substation B is taken, the value is taken at 10:30 05 seconds. So you can see that there are 5 seconds time gap. So these data are not real time, are not synchronized. This is the biggest inadequacy of the SCADA system. And especially for the very large scale power grid, this time difference, this time in synchronization will be inaccurate for system real-time state estimation or real-time analysis. Okay. Another inadequacy of the SCADA system is that the sampling rate is very low. You can see that every 2 to 4 seconds, a measurement is taken. However, you should understand that for power system, the dynamic behavior of the system dynamics has a very short time interval, sometimes in the range of milliseconds, okay, not to say the seconds. So 2 to 4 seconds is too long to understand or to monitor the power system dynamics. Okay. So SCADA system cannot provide dynamic information of the system, especially during the disturbance and the transient event. So in the first lecture, I have briefly introduced the power system security, right? Generally speaking, the security can be divided into static security and dynamic security. Well, for dynamic security, it mainly concerns on the system dynamics. And if you can remember that the stability can be further classified into rotor angle stability, voltage stability, and frequency stability, right? And these all stability criteria, they have a relatively short time interval, especially for the transient stability. The system can become unstable within just 0.1 second, okay? And for the short-term voltage instability, the same. The voltage collapse can happen within less than 1 second. So if we use SCADA system to control or monitor these stability issues, it is inadequate because the sampling rate is longer than the system dynamic changes. So that is another drawback of the SCADA system. So the SCADA system can only support steady-state operation and control. As I just said, after we collect this voltage magnitude, real and reactive power, we can do the system steady-state security assessment, and we can do the system dispatch, power flow dispatch, network reconfiguration, so on and so forth. But this is all for steady state analysis, not for the dynamic. Okay. So to summarize, the real-time control is impossible. Real-time control is impossible when real-time system measurements are available. Okay, so we need to have the real-time measurement to do the real-time control and the dynamic analysis for the power grid. That's why we need to have the phasor measurement unit. So by its name, phasor measurement unit is to measure the phasor, right? By its name is to measure the phasor quantities of the power grid. So what is the phasor? Let's take a quick review. This concept was very fundamental for the AC electric system, right? For the AC system, we have sinusoid waveform for voltage and for the current. If our power grid frequency is 50 hertz, then this sine wave will have a 50 hertz frequency. Every second, it will change 50 times for its direction and magnitude. Okay, so basically, we can use this cosine item to denote the AC form. Okay, in time domain, this is a voltage trajectory. Okay, it's a voltage trajectory in time domain on the left figure. So it can be denoted as magnitude V. V is the maximum value of this sinusoid waveform times the cosine item, 2 pi f plus sigma. Okay, the f is the frequency. Okay, f is the frequency. And the sigma is actually the initial value of the, the starting value of the waveform. Okay, starting value of the waveform. Actually, it is the angular starting value of the waveform. Okay, take this as an example. You can see that initially this is a phase angle, sigma 1. All right. So this is the time domain representation of the sinusoid waveform. While in the phasor representation, we can directly use its magnitude V and its angle sigma to denote this phasor value. Okay, to denote this phasor value. Here we do not put frequency anymore because we assume the whole system has same frequency. Okay, has the same frequency. So you can see here in the phasor representation, the voltage magnitude is here is diameter, okay, of the circle, and the sigma is the initial value, starting value of this complex number, right? You can see that it's an angle difference between this phasor arrow and the y-axis. So basically, phasor means the both voltage magnitude as well as the phasor angle. Okay, as well as the phasor angle. So the angle is very important because it is a very important indicator of the system dynamics. Okay, of the system dynamics. So later on, I will also show some, the videos to better understand this angle, phase angle. So how can we measure these phasors? Basically, we have this so-called phasor measurement unit, PMU, as shown here. You can see it is a small box. In my own research lab, we have also installed such a PMU in our lab to measure the frequency as well as the voltage phasor. Very importantly, okay, each PMU will measure the phasor at a connection point. But remember, at the beginning, I have mentioned, we want to have the time synchronized measurement, right? All the phasor values, we want to make it synchronized. So the synchronized phasor are called time synchronized measurements of a certain parameters of the power grid. So this PMU, once they are connected in the grid, they have a function to be synchronized by GPS, by the GPS. So every phasor measurement will be synchronized and become synchro phasor And the phasor can also, based on the phasor, we can also estimate the system frequency. Okay, we can, because you can see that the frequency has a relationship with this phasor measurement, so we can also measure the frequency as well. Now, the PMU in practice, they can measure synchronize the phasor, the frequency, as well as the rate of change of the frequency, estimate from the void and the current signal, and a time synchronizing signal. Okay, so this rate of change of frequency, RECOF, is also a very important value because it measures how fast the system frequency will change following a disturbance. Okay, so this is very critical for frequency stability assessment. Okay, now once again, you can see that the frequency, the PMUs, after installed at different locations, they are synchronized by the satellite GPS. Okay, by the satellite GPS. So the working principle is that the satellite they will issue the time synchronizing signal for different PMUs, and after receiving this synchronizing signal, it will, the measurement will be adjusted against the same time stamp so that the measurements are time synchronized. So that is the basic principle. Okay, to summarize, the PMU measure voltage, current, and the frequency, and they can calculate the phasor angle. Now, each phasor measurement is time stamped against the GPS universal time. So once phasor measurement is time stamped, it will called a synchro phasor. And certainly this synchro phasor can have a lot of applications because it represents the system dynamic status. Later on, I will give you a more detailed introduction. Now, it's time to compare the difference between the SCADA system and the PMU system. Okay, you can see that we compare in different aspects, including the sampling rate, the measurement quality, the time synchronization, as well as application. Okay. Now, for the SCADA system, the sampling rate compared with PMU is much lower. Every 2 to 4 seconds, it will take one sample. So it can only support steady state observability. And the measurement quantity is just the magnitude of the voltage and the current. There is no phase angle at all. And very importantly, these values are not time synchronized. Okay, are not time synchronized. They are actually taken at the different time intervals. Okay. So the SCADA system is mainly used for static monitoring and control. Okay. That is for steady analysis. A PMU is different. First of all, its sampling rate is very high. You can see every 1 second, it will take 10 to 60 samples. Okay, compared with SCADA, you can see it is most 100 times higher in terms of the sampling rate. And importantly, it can take measurement of both magnitude and the phase angle as well. Okay. So, and the values are synchronized, time synchronized. So it can support the wide area real-time monitoring and control. The wide area here is very important because these measurements taken at different remote locations, they are synchronized against the same time. So the whole system can be analyzed over a wide area horizon. So that is why PMU is mainly used for wide area real-time monitoring and control. So based on the PMU, the system can measurement system can be formed, so-called wide area measurement system, so-called WAMS. Okay, WAMS. I suppose many researchers or professors You may recall that back to probably 15 years ago, the WAMS is one of the most hot topic in academia and even in the industry. Right? At that time, everyone is doing WAMS-based control, WAMS-based protection, WAMS-based system estimation, dynamic estimation, and advanced dynamic studies. So that is all based on the PMU technology. Okay, now we can take a look at a realistic measurement of the SCADA system and the PMU system. So these two figures are extracted from this report, NERC, North American Reliability Council. Okay, in 2010, they published a report called Real-Time Application of Synchro Phasors for Improved Reliability. Okay. So in the upper figure, this is the SCADA measurement. The graphs actually are frequency of the power grid. Okay, you can see that this whole time horizon is around 10 minutes. Okay, from 8:10 to 8:20. Okay, so the sampling rate is about 4 seconds. Okay, 4 seconds value. Now you can see that over these 10 minutes, the frequency was fluctuating a bit. Okay, especially during this range. Then after that, the frequency gradually increased. However, it has not increased much. If you look at the y-axis, it ranges from 59.9 to 60.06. So actually, the frequency just fluctuates within 0.05 seconds, which satisfy the operation limit. Okay, so in most of the countries, the frequency variation tolerance is plus minus 0.05 hertz. Okay, hertz. Then you can see that after that, the frequency increased a little bit. Then after that, it starts to recover, and but always it stays at a secure range, 60.06 to 59.96. Okay, it's satisfy the operation limit. Okay, so that means if we just look at the SCADA system, okay, everything is fine. Right, everything is fine. The frequency is very good. They are always within the operational limit. Right, so this is observation from the SCADA data. However, in the meantime, we also have the PMU measurement, and this PMU measurement, okay, this figure, this window shows the very small time horizon within 4 seconds here. Okay. So these values correspond to the very short time horizon circled here in the blue box. Now, if you look into the PMU measurement, what can you find? You can see that during this period, there was a very dramatic frequency decline, right? It declines to how much? Declines to 59.9 hertz. Okay, it declines from the 60.02 to 59.9 hertz, which is a very big drop. And actually, it is already beyond the operation limit because our limit is 59.96 here. Right, so during this very transient period, actually the frequency is over range. And after that, you can see the frequency recovers back, but follows followed by oscillation. Right, you can see the frequency oscillates significantly, although in the end it recover back to the normal. However, this transient event was not observed by SCADA system, right? Because the sampling rate is too large, it's every 4 seconds, and this happens within just 1 second. Okay, so If we want to detect such transient, such a very fast dynamic behavior, we have to use a PMU data. And very importantly, if we only use SCADA system, the power grid seems to be okay, everything to be okay in terms of frequency. But if you view the system, monitor the system from the SCADA PMU system, you can see actually there was a transient event. Okay, there was a transient event. So that's why we have to use the PMU to understand and monitor the system dynamics. Now, the values of synchro phase measurements, there are a lot of values. They have a lot of applications. So to summarize, first of all, the phasor data can support grid operation and planners to provide unprecedented insights into what has happening on the grid at a high resolution over a wide area in time synchronized mode where needed and in real time. Okay, this one we have already explained. It can support the very high resolution and high sampling monitoring of the system dynamics, right? And the SCADA system observe grid condition every 2 to 4 seconds, which is too slow to track the dynamic events happened on the grid. We also don't monitor key indicators, especially the phasor angles. So later I will show the phasor measurements and give you a sense about how these phasors can indicate the system dynamics. And the SCADA system, SCADA data are not consistently time synchronized and time aligned, and those data are not shared widely across the grid. This is also an important concern. The SCADA system, okay, for the large-scale power grid, which contains many, let's say, regional grid. So each regional grid may have its own SCADA system, and this SCADA data may not be shared among different regional grids. So we cannot analyze the whole system, the whole grid as an entire dynamic system. Okay, that's why the PMU, since they are able to collect the time synchronized values over the wide area, so they can support the system to monitor and control at the entire system level. That is a very important advantage. So the wide area visibility, right? Wide area visibility is the important value provided by synchro phasor. And so synchro phasor will allow the collection and the sharing of the high-speed, real-time, time-synchronized grid condition data across the entire system. This data can be used to create wide area visibility, as I just said, across the whole, the bulk power system in ways that let grid operators understand real-time conditions, see earlier evidence of emerging grid problem. This is very important. This is a so-called early warning. Okay, you can see that according to these measurements, if we have PMU data, then clearly there was a transient event happening. So based on this, we can make earlier warning to the grid operator. There must be some faults or some, event happened. So based on that, we should prepare the system. We should kind of preventively control the system in order to withstand this disturbance or coming different contingency events, and can also better diagnose the fault. Very importantly, based on this measurement, we can do the post-event analysis, right? So we can try to understand what happened that make this frequency dramatic decline and oscillation. Then based on this measurement, we can fine-tune the system dynamic parameters. Okay, so later I will also give you an example. We use, PQ, power quality data, to estimate the load parameters. Later, I will introduce this. Okay, so to implement and evaluate remedial actions to protect system reliability. That is what I have mentioned, the WAN-based protection. Okay, the protection system over the entire grid can be based on this PMU measurement. So, traditionally the protection devices, they are kind of locally set, locally programmed. They do not coordinate with other protection systems over a wide range, right? Sometimes it may only communicate within a substation or communicating with a neighboring substation. They cannot communicate with very remote substation. But the PMU can do that, right? Based on the PMU, this protection system, they can coordinate at the entire system level. So this will clearly improve the system reliability. And applications, okay, a lot of applications for both real-time operation and for offline planning. Okay, so later I will introduce two examples. Okay, two examples. For the real-time application, you can see here we have a wide area situational awareness, right? Based on the measurements, we can estimate the system condition and clearly including the frequency stability, the power oscillation, the voltage monitoring. They are all dynamic parameters that can be monitored by the PMU system. And we can do the alarming and setting properly the operating limits for the system. We can also detect the events, and we can also eliminate the impact of the contingency event. And we can also do the dynamic state estimation. Okay, traditionally the state estimation is based on SCADA system, so it is only steady state estimation. But now, if we have PMU measurements, we can do the dynamic state estimation. Okay, so we have a more accurate picture of the system. And we can also do the dynamic line ratings and congestion management. What does that mean? We can, real-time monitor the power, phase angles of different transmission lines. And based on that, we can estimate how much capacity is remaining for the transmission line. So that is so-called dynamic line rating. And outage restoration. Okay, we can also, quickly restore the outage because we have a full visibility of the system. So that are mainly for the real-time operation. And the offline application or the planning application, what can we do? Certainly we can do the baselining of the system performance, just like this. Okay, if you just look at the SCADA system, okay, the system is performing well, very well, but using the PMU system, we will realize that the system still has some issues. So we can do this baselining for system performance. And we can do the post-fault, post-event analysis. Based on the measurement, we can try to understand what has really happened. Was this a frequency oscillation caused by a short circuit fault or malfunctions or what else? Right, a steady state model calibration and validation, and the dynamic system model calibration and validation. This is very important because for the power system analysis, we need to have the system model, and for system model, sometimes the parameters are set by default or set by kind of manufacturing at the manufacturing phase or provided by the vendors. Okay, so these model parameters sometimes are not accurate. Even they are accurate, sometimes they are still vary from time to time, and also depending on the operating condition, right? Yesterday, we have answered the question about the uncertainty of line parameters. Even the line parameters, resistance, reactance, they are also time vary, depending on the temperature, okay? So we want to, calibrate and validate these parameters. But in order to validate and calibrate, we should have the measurements. Right, so this PMU measurement provides a very, very useful data source for us to do the calibration. And certainly we can also validate the model of the power plant. So we can model the load as well. So later on, I will introduce one application for the load parameter estimation. And the special protection scheme and landing. Based on this, we can set the protection scheme. We can program the protection parameters as well. And the primary frequency governing response, okay, we can also set for the frequency control system based on the PMU measurements data. So you can see that the PMU have so many applications. Now, in this lecture, I will mainly introduce two applications. One is for the stability assessment. Another one is for load parameter estimation. Okay, one is for real-time application, one is for offline application. Okay, and all right, it's 35 minutes already. So before we move ahead, let's have maybe 5 minutes break. Okay, 5 minutes break. Please come back after 5 minutes.
Okay.
Okay, hello everyone. So let's go back and continue with the PMU measurement applications. So I will today introduce two applications. The first one is the so-called data-driven stability assessment. So based on the name, you can understand the assessment of the stability is based on the data. Okay, and certainly the data is the PMU data, right? So here, this is a illustration of the root angles of a power system after a fault disturbance. Now, I suppose everybody understand the concept of the root angle. The root angle actually is angle difference between the, generator basis voltage as well as its internal voltage E, right? So this root angle actually is a very important dynamic parameter, indicating the stability of the system. Because in reality, during the operation, we need to make sure that all the synchronous generators, they have the synchronized, their root angles are synchronized. Okay, their root angles have to be synchronized during the operation. Now, but in practice, sometimes the fault will happen. For example, a short circuit fault. And after the fault the fault, the root angles of different generators, they will change over the time. Now, this is a simulated root angle trajectory. You can see that the fault happens at 0.2 seconds. And after that, you can see several generators, their angles continuously grow. And some other generator root angles, they will still stay with each other together. But after 1.4 seconds, okay, at 1.4 seconds, you can see the generator root angles, they diverge into different groups. In other words, they lose synchronism. Okay, they lose synchronism. And if this has happened, the system become unstable. Okay, the system become unstable. The protection system will be triggered and will trigger off the generators, and we may also separate the power grid into different areas, and which in the end lead to the outage, okay, lead to the blackout. So in this case, this is an unstable case. Now, question is, how can we preventively evaluate this instability? Now you can see that these trajectories are simulated on my computer using PSSE software. Right. In the first day, some students asked me which software do we use. So at NTU, we are using PSSE. So in order to simulate this 1.7 second dynamic trajectory, we actually consume 2.2 seconds CPU time. We consumed 2.2 CPU time on computer in order to simulate just a 1.6 second trajectory. So my point is, okay, if the fault has just happened, and as long as we know the fault happens, we start to use the simulation. We want to simulate whether the trajectory will diverge or converge. You can see that the simulation is not fast enough, right? The system is already unstable before we finish the simulation. Okay. So that means if we rely on computer simulation for stability assessment, it will be too late for the online analysis. But certainly this computer simulation can support offline analysis. At the offline stage, before the fault happened, we can certainly simulate different faults and observe the trajectory. But that is for the offline analysis. For online applications, the simulation is not enough. So what if we want to online evaluate the system's stability? Okay, just after the fault happens, we want to immediately predict whether the system is stable or not. What can we do? Now, very straightforwardly, we can actually use some initial measurements of the root angle to predict its future status. Now, this is the illustration. Okay, this is another simulated root angle trajectories. You can see that, okay, the fault happens. during this time period. And after the fault is cleared, we start to, we use the PMU measurement data for a certain time window. And this is called observation window. And based on this observed PMU data, we can do the prediction. We can directly predict the future status of this root angle, whether they are converged or diverged. It's just standing at this time point, so that we don't need to simulate them at all using computer software. We can directly predict. So you can see that at this observation time window, we can directly predict the future status of the system stability condition. Okay, and this is a so-called data-driven stability assessment, because we don't use any simulation during the online stage at all. Okay, we just do the prediction. But the question is, how can we predict? How can we accurately predict the trajectories will diverge or converge just based on a small observation time window? Okay, so in our research group, we have been working on this topic for more than 10 years. You can see here, 2013, we have published a kind of a magazine article to introduce this WHO approach. Basically, this approach is based on the artificial intelligence, the machine learning. So we call it intelligent system-based method. Now, basically, the method consists of two stages: the offline stage and the online stage. At the offline stage, first of all, we need to have a stability database. And this database will contain numerous trajectory, root angle trajectories, void trajectories of both a stable case and unstable case. So we have such a database. And then we have to define the input and output of the machine learning model. So basically, the input is the measurement, PMU measurements after the disturbance. Okay, so we use the post-disturbance variables as input. And the output of the machine learning model certainly is the stability status. Okay, it can be a binary value, let's say 1 or -1. 1 stands for stable, and the -1 stands for unstable. Okay, so after defining this input and the output, we can train a machine learning model using this stability database. And this machine learning model will be in the form of a classifier or kind of regression model, depending on the output being binary, class level, or being continuous value. And during the machine learning stage, we can also extract other relevant knowledge from the machine learning process. Okay, so this is for the offline stage. And after the machine learning model is well trained, we can directly put it for online application. And during the online stage, every time interval, we have the PMU measurements, right? Then this PMU measurement will be imported as the input to the classifier or predictor. Now the classifier and the predictor will immediately predict the stability status. Okay, so actually this prediction or this classification is instantaneous, because the artificial neural network, other machine learning models, the calculation is just based on some straightforward matrix operation. So they can directly give you a output within 0.0, even 0.1 second, very, very fast. Okay. And based on the stability assessment results, we can do the control, either preventive control or corrective control. And besides, the extracted knowledge during the offline machine learning process can also be combined or used during this decision-making process. Okay. Now, so this is the general principle or architecture of this data-driven, intelligent system-based data-driven stability assessment. And the advantages is they are very fast, right? They are very fast. As I said, it only takes just less than in the millisecond time range, it can give you output. And the feature, other and it requires much less data requirement because it only requires PMU measurements. It does not need other measurements to do such prediction. Well, while this general principle is straightforward, we have to develop key technologies to realize this, which include the feature selection. Okay, how do we select the most, useful PMU measurements as the input? Because PMU they installed as a power grid at different locations. Not all of them are useful, or not all of them are equivalently useful for the machine learning model. So we need to select these most useful, most significant features. And certainly we need to develop machine learning algorithms. Nowadays, people are talking about deep learning, right? Many advanced machine learning algorithms, so we can apply them as well. And also we need to make intelligent decisions based on the stability assessment results and other knowledge. What type of control can we design? That is also an important topic. Now, as I said, our research group have been working on this back to 2010, actually. So far, it's almost 14 years already. So we have developed many methodologies to realize this intelligent system. Specifically, we need to properly generate a comprehensive stability database, because in order to train a machine learning model, the stability database is always most important. If the database is not good, you can imagine the machine learning model will not be good either. And we need to select and extract the critical features, as I just mentioned. And we need to evaluate the credibility of the model output. What does that mean? The machine learning model, sometimes they may have prediction or classification error. That's why that means in reality they cannot maintain 100% accuracy. Right? This is very normal. Everybody, if you have experience in using machine learning, the accuracy is always an issue. For power system stability assessment, the accuracy is certainly critical, because if you make a wrong decision, it will affect the system significantly. Right? So we have to evaluate whether this machine learning model can give you a credible output or not. So this is a very important concern. So in our group, we have also developed some credibility criteria. Okay. And we need to improve the accuracy and the speed. Okay, because you see here the the observation window, we certainly don't want to observe too much, too long. Otherwise, it will waste time for the control later. So we want to use minimum observation data to predict the results. So we have to balance between the speed and accuracy. And we want to extract the knowledge for stability control, as I also mentioned. And we also want to update the model timely and effectively. Here you can see we have this dashed line. Because the model was originally trained by one stability database. However, for the online application, sometimes the system may have some unexpected changes, which are not reflected in the stability database. So we have to update this model from time to time. And we have to update the model timely and effectively. That is also a requirement. And besides, the PMU measurements, as well as communication systems, sometimes they may also have some abnormal data, including the missing data, and they may also have time delay, communication delay. So when the data is missing or the transmission is delayed, the signal transmission is delayed, how can this machine learning model work? So we also need to consider these issues. Okay, and last but not least, when we train a machine learning model, we normally will consider kind of a certain range of the faults, but we cannot exhaust all the faults, right? Because essentially the number of the potential faults are infinite. Okay. So when we train a machine learning model, we want to transfer it to different faults or different system topology. Okay, so we have to adapt the model to unforeseen scenario. That is also a requirement. So you can see in our research group, we have been working on these topics, and we have published our research works in these papers. Okay, so until most recently, we also have 2 papers just accepted. And we have summarized our methodologies in this book. Okay, this book was published back to 4 years ago, 2020. This is a summary of all of our research works in this area, the data-driven stability assessment. Okay, I want to let you know that these references are actually optional. Okay, you don't need to go through them because it is very beyond the requirement of this course. But I just show them in case some of you are interested in this topic, and in case you are exactly working on similar topics, because this one is a very hot topic since many years ago. Okay, many researchers, they have been working on similar topics. They are also using most advanced machine learning algorithms, the deep learning, right, and many other machine learning techniques. So if you have time, please take a look. So that is the first. Application of the PMU. Okay, based on the PMU, we can develop the artificial intelligence model and directly predict the system stability. That is for the online applications. Now, how about the offline application? Just now, I have shown here for the offline study based on the dynamic environments, we can calibrate and we can validate the models, including system models, power plant models, load models. Okay, so back to many years ago, when I was in Australia, maybe 10 years ago, we had a project with a local utility company. The purpose of this project is to estimate the models of their loads in an industry region. Okay, in that region, there are a lot of mining loads, mining motors. You know, the mining, they are kind of using the motors, very heavy motors, to do the mining jobs. So for that heavy motors, you know, they consume a lot of reactive power. And as a result, the voltage quality and the voltage performance are not that good. So this utility company, they want to place a dynamic voltage resource device called StatCom, okay, to improve the voltage stability and the voltage quality. But before that, we have to model the load, their dynamic load parameters. We need to figure out how much how much motors and other components are there connected to that industry region. So how can we do that? How can we estimate the load components? The most straightforward way is to do a customer survey, right? We go to the customer site, we ask them how many motors do they have, what are capacity of their motors, and what are their parameters of each motors. Now, after we get all of them, we can do a kind of entire model. But clearly, you can see this is not efficient, and sometimes not impossible, not possible, because sometimes they do not know the detailed parameters of their motors anymore, and sometimes this total load is a mix of different motors, lighting system, and other types of the load. So it's not easy to do such a customer. Instead, we can actually directly use the measurements, dynamic measurements, to estimate the load parameters. Okay, so that is what we did in that project. But instead of the PMU data, what we used is actually the power quality data. Now, power quality data can also, this power quality device meter, they can also measure the voltage, real power and reactive power with a very high sampling rate, So you can see here, I listed the voltage curve and the real power curve after a kind of disturbance in this region. Now the red curve are realistic values. You can see this is the voltage. Originally, it stays around 1.0 per unit. After a disturbance is suddenly decreased to a low level, 0.8 something, then it sustains for some time. And before the fault is cleared, after the fault is cleared, the voltage start to recover, right? The voltage start to recover. Okay. And correspondingly, this is a real power fluctuation, real power changes during this disturbance. Okay. So our approach, our idea is that if we have a load model, we want to estimate its parameters. So if we can optimize these parameters to minimize the simulated voltage and power curve with the measured voltage and the power curve, then the optimized parameters, load parameters, will be the one close to the reality, right? I hope you can understand this. We try to optimize a set of load parameters, so these load parameters can reproduce a very close voltage and the power curve with the measured curve, so that we can get this load parameters. So this is a general idea. Now, first of all, we have the load parameters, right? We actually we start from here, right? We have the measured PQ and V trajectories, and then we use original load parameter. Sorry, we start here. We set original load parameters. Then we do dynamic simulation. We can simulate the PQ V trajectories. And then we compare the simulated trajectories and measured trajectories. Now there will be a fitting error. Now our objective is to optimize these load parameters to minimize the fitting error. And the optimized parameters that can lead to the least fitting error will be the one of the parameter set. Okay. Now here you can see this is the result. We have done this is one substation. Okay, one substation. Actually, two substations. Sorry, two substations. You can see that we have for two substations. You can see the percentage of different different load components are different. They have large motor, small motor, charging, discharge, lighting, constant power, remaining loads. They have different portions. Okay, and these percentage values are actually optimized through this progress. Okay, so this whole method is actually published in this article, and based on these dynamic load parameters, we can optimize the required size and the site of the StatCom in order to improve the voltage stability. In order to improve the voltage stability. So that is what we can use, what we can apply the dynamic measurement data for model parameter estimation. Okay, that is the second application that I want to introduce today. Okay, so that is the end of the lecture slides. Then I want to show some websites to help you to understand understand the PMU measurement. Okay, I will show a website later on. Wait a second. Okay, so here, you know, in USA, University of Tennessee, they have such a platform to show the phasor measurement unit and their real-time value installed in USA and globally. Now here, I can quickly show you here. This is the table display of the PMU measurements, actually the frequency measurements collected from different units. Different colors stands for different frequency deviation. Okay, deviation. Now you can also see this is frequency plot of different units over the time. Right, this is a frequency measurement, and then this will be a phase angle display. Now here you can see the different color represents the different values of the phase angles. Now you can see the dark one stands for the small value of the phasor angle. The red one stands for higher value of the phase angle. Now you can see clearly for this part, USA eastern part, the middle part has a higher phase angle value, and the eastern part has a lower phase angle. Based on our fundamental knowledge, right, the real power will be transmitted from high angle area to the low angle area. So according to this, we can immediately understand there are power generation transmitted from middle area to the eastern area, because eastern area is a load center, right? So this is immediate kind of a observation. And the frequency gradient map, okay, you can also see the frequency deviation in different ranges. They are all measured by PMU. Okay, and they also report the worldwide frequency measurement. As long as the unit is installed and communicated with their platform, we can show this value in real time. Let's give it a few seconds to show spectrum. Okay, so this is to show the, estimation accuracy, time error, and the sample events. Later I will show sample events to you. Okay, you can see here, this is a worldwide frequency measurement. Okay, you can see they cover North America, Europe, China, India as well, Australia, and even Singapore. We also upload our measurement to this website as well. Okay, so they are very interesting. You can go to this website to play and to see. Okay, now I want to show some blackout events you see during the for the frequency measurement. Okay, so you can see this is a blackout. Let's see what does the frequency look like. Okay, you can see here. Initially, the frequency stays around 60 hertz. Right? After that, suddenly there is a disturbance. The frequency drop to 59.96. Then it stays at this low level for a certain time. Right? Then after that, stay here for maybe longer than 10 seconds. After that, the protection has triggered. It may cut off some load, okay, shed some load. Then after that, the frequency start to recover immediately back to 6. Then after that, system primary control has acted. Then the frequency finally recovered. Okay, so this is also measured by PMU for the frequency. And there is another event. It's a blackout. You can see the frequency dramatically decline to a low level. Okay, each curve represents one frequency measurement unit. Okay, you can see very clearly here. And another event caused by a tornado event. You can see that the frequency fluctuates significantly because of the tornado. So my understanding is that this area may have a lot of wind power. So this tornado will change the power output of the wind turbine, which in turn change the frequency. So you can see the frequency start to fluctuate very significantly. Okay, so very interesting. This is for the event. So you can go to this website to check these values. Okay, different regions, right? Okay, so that is all for the lecture. For now, let me see any questions. If you have any questions, please type into the chat box. Okay, the first question is, how can we mitigate communication delay? Yes, so for the control purpose, theoretically speaking, the communication will also contain delay, right? So there are two ways. First way is to compensate the time delay. Okay, to compensate the time delay. The second way is to design a communication tolerant, delay tolerant control system. So in our research group, we have designed this compensation-based control system, which take into consideration of the time delay. And during the control design stage, we add a compensation unit. This unit can cope with this time delay. Because essentially the time delay will, for dynamic perspective, the time delay will lead to instability. If the time delay is beyond a certain kind of limit, the system will become unstable. So it's very important to consider time delay. How can we integrate PMU to grid to help prevent blackouts? The real world example is just like this. You can see that if we can have an early warning, right? If we can have this early warning, if we can have this early warning, so if such event happens, if we can early predict the instability beforehand, so we can immediately take the control actions. We can immediately trigger the generator. We can shed the load. We can even separate the system so as to prevent the blackout. So that's why back to many years ago, the wide area measurement-based protection is so hot because they want to make use of this PMU to set their protections and to do their system controls. What are limitations of traditional SCADA in modern? I think this one we have already answered, right? The SCADA system is like can only support steady state analysis. I think this one has clearly compared. We have clearly compared the adequacies of the SCADA system and how PMU is better than SCADA, and what is the values of the SCADA system, PMU system against the SCADA system. Is it wireless? Okay, the PMU is actually communicated installed at the power station. So the signal are transmitted among each other through the power line communication or fiber communication, but they are synchronized by GPS. Okay, you have to know that they are synchronized by GPS. Here, the timestamp are actually synchronized by GPS, but they are essentially communicated through wired communication. You can see here. I remember we have mentioned it somewhere. Yeah. So this is the PMU measurement is communicated with wired communication. To use Smith predictor, you mean for which part? For which part? For Smith predictor. Okay. For communication, yes, certainly there are different methodologies for predictor. Yes, the compensator, a lot of. How to measure the row curve using PMU. Yes, you know the raw curve is actually the change rate of the frequency. So as long as you measure the frequency, you can directly calculate, right? You can directly calculate the delta F over delta T, delta F over delta T. So it's very straightforward. It's just a delta F over delta T. As long as you have the measurement, you can certainly calculate that. Yeah. The network has latency, so it may be. Yeah, for SCADA system, SCADA is mainly for steady state analysis. So the time delay is always there because every 2 seconds are always there. But for steady state, we don't concern too much on such time delay as long as it's within, let's say, seconds level. For the PMU, because it's for the real-time analysis, so the time delay is critical. So we can either compensate the time delay at the device level, or we can design the delay tolerant control system. Both of them are okay, actually. Yeah. Both of them can be applied. Okay, any other questions? Oh, all the signals are synchronized. You know, PMU actually essentially is to it will receive time stamp. It will receive. You can see the phasor measurement is time stamped against the GPS. So all the values are synchronized. V, angle, yeah, frequency. They are all time synchronized. Okay, any more questions?
So, Yanju sir.
Yes.
Yes, sir. As you already highlighted, for synchrophasor simulations, CPU time is taking very high, more than 2.2 seconds you mentioned.
Yes.
Okay, so and we have to simulate very quickly. Then, which system would you suggest to use for synchrophasor simulations and analysis or wide area measurements? Because as you told, we have to do in real time. We have RTDS, real time digital simulator, or whatever.
Yeah.
Which system will you suggest to use for wide area monitoring, situational awareness, and synchrophasor data analytics, and many things? That's all.
I think yeah, RTDS and OpenRT, they can certainly do this job. In our research lab, we use OpenRT. Yeah, we use OpenRT, but the RTDS is the same. Yes, they can do the real-time simulation, and they also have interface with the PMUs. You can install with them. Yes.
Is there any other system, sir, other than this OpenRT, RTDS, which
For
use?
the offline simulation, actually we use the PSSE. Then we set a very small timestamp, 0.01 second timestamp for simulation. That is also possible, and you can also use Power Factory. You can also use a PSCAD for electromagnetical simulation. So they can also support very high resolution transient simulations. Yeah, PSCAD is also useful. Yeah, one question is, smart meter contribute to harmonics? Actually, no, because essentially it's just a meter. It's essentially just a meter. It does not contribute to harmonics. Harmonics is mainly generated by the converter, by the high switching power electronic converter system. Yeah.
Sir, is there any open source data available for WAMS analysis where we can get the data, ready-made data? Because getting PMU data is becoming very challenging day by day. Do you
Yeah,
have
I think you can go to the website I just shown here. This one, there are a lot. They publish a lot of data. You can see here. This one, I guess they provide the open data, open source data. Yeah. Here you can go to this website. Yeah, you can go to their website and have a check. Yeah, I guess there are some data. Okay.
Thank you, sir. Thanks a lot, sir.
Okay, thank you. Yeah. Then after this, I think Professor Kumar will cover another session, power converters. Right? Yes. Power converters. So we can have, maybe you can have 5 minutes break if you want.
No, sir. It is 1 hour break.
Oh, 1 hour. Okay. That's fine. Okay.
Thank
you. Another question for real-time simulation, MATLAB simulation be used? Real-time simulation, no. The MATLAB and the Simulink, they only support the digital simulation. If you want to run it in real time, you have to connect it with OpenRT RTDS. So for OpenRT, the simulation package RTLab actually support MATLAB. They are essentially very similar. So if you have your MATLAB codes, MATLAB models, you directly, implement in RTLab, and then you simulate in OpenRT, then it will be real time. Yeah. Okay, thank you.
Thank you.
Yeah, in afternoon, I will introduce energy storage technologies. Okay, energy storage technology is very, very important in smart grid. So I will introduce that portion. Okay.
Thank you, one and all. Thank you, Professor Yanzu. Again, meet again at 10:30 a.m. Which is power converters in smart grid application, which is going to deliver by the local speaker, Dr. D. Srinivasarao. When you please join again back at 10:30. Thank you, Professor.
Okay, thank you, guys. See you afternoon. Bye-bye.